Alright, welcome to Chapter 9, Part 2. This is Module 12. Alright, and so we have been talking briefly about molecular geometry. And now we're going to attempt to explain covalent bonding and orbital overlap. Now we can first start talking about valence bond theory as a model of covalent bonding. Okay, but what do we mean by model? Well, the VSEPR model does not explain why bonds exist between atoms, but just provides a simple means for predicting the molecular geometries. Now, if we remember that the bonding electron pairs are concentrated in the regions between atoms, and that covalent bonds are formed by sharing electrons, then we know that this can occur only when the valence atomic orbitals on the two atoms are going to overlap. Thus, the shared electrons reside in these overlapping orbitals. Okay? And because of this overlap, electrons are attracted to both nuclei and hold the atoms together. So here we can think of two hydrogens, those come together, and that overlap is where those electrons are being shared. Okay? In a different example of hydrochloric acid, where you have a hydrogen bond to a chloride, chloride has its valence electrons in these 3p orbitals, which are going to overlap with a 1s of hydrogen, and that overlap there is where those electrons are being shared. Okay? If you had Cl2, basically, once again, you'd see those two 3p orbitals overlap, and in the middle there is where we have our electron density. So, in a covalent bond, the distance between the two nuclei must be at an optimum distance. Okay? And so as the atoms are far apart, as shown in this figure, they don't really feel one another. Okay? And so the energy is near zero, this potential energy. Well, as that distance starts to close, the s orbitals are then going to start to overlap. Okay? The potential energy of the system then decreases, okay, because of the increase in electron density between the nuclei. And so you have the strength of the bond is actually increasing as these get closer. Now what happens is if those atoms get too close together, then that energy is going to quickly rise due to that increasing electrostatic repulsions, okay, between the nuclei. Remember, these two nuclei, they're getting closer and closer together. If they get too close, now they're going to really have that potential to really push away from one another. So bond length is the distance that corresponds to the minimum of that potential energy curve, which is shown here. Okay? And thus the bond length is set by the balance of both an attractive and those repulsive forces. It's really a balancing act between those two. Now, if we take a look at the atomic orbital of carbon, okay, we know that the valence shell of carbon has 2 electrons in the s orbital, right? We depict it as a circle, and 2 electrons in the p orbitals, okay? And so that's based on, we have a 2s2, 2p2 in the valence, so we have 4 valence electrons. Now, if we think of methane, which is CH4, okay, and we look at the VSEPR model for geometry, we see it has tetrahedral electron domain geometry and molecular geometry, and is shown here. Okay? But the question arises is, how do covalent bonds formed from just overlapping atomic orbitals, and these are just overlapping with hydrogen atomic orbitals, result in the molecular geometry described here in the VSEPR model? Okay? Well, what we have to remember is that atomic orbitals are just mathematical functions, okay, depicted as just a pretty picture. Okay? So either a circle or these nice balloons, which really predict the probability of where an electron may be. So in covalent bonds, you form what we call hybrid orbitals. Okay? Hybrid orbitals are just separate atomic orbitals that are mixed together to form new hybrid orbitals. Okay? So the process of mixing different atomic orbitals, like the s and the p's, is just a mathematical function called hybridization. Well, to really illustrate the process of hybridization, we can look at beryllium. Okay? In its ground electronic state, beryllium would not be able to form any bonds, right? Because it has no singly occupied orbitals. Everything has pairs, 1s and the 2s. But if it was to absorb just a small amount of energy and promote an electron from that 2s to the 2p orbital, now it has the ability to form 2 bonds, okay, one with each of these. And so what happens is we can actually form beryllium F2, okay? So 2 fluorines coupled to beryllium, okay? However, one electron is in that 2s and the other is in the 2p. So they wouldn't be identical, okay? So the 2s and the 2p orbital are mixed together to form what's called an sp hybrid orbital. Okay, so we can kind of take a look at that here. Okay, so here we have an example of BeF2. Okay, and these hybrid orbitals are just created by either mixing these different atomic orbitals, s, p, d, to really match that electron domain geometry of a compound. So we said that the beryllium, we could push one electron up to the p orbital, right? So that means we have one in the s atomic orbital and one in the p atomic orbital. And if we mix one s and one p atomic orbital, these hybridize to form two sp hybrid orbitals. And this is a sp hybrid orbital. We have two of those. Okay. If you lay those on one another, basically you form what's shown here. Okay. And this, by mixing this s and p orbital, you yield two degenerate orbitals that are hybrids of the two other orbitals. Okay. So now what happens is the two degenerate orbitals, okay, would align themselves 180 degrees from each other, which are shown here in purple, okay. And then basically the fluorine, which has a p orbital which has only one electron, is going to overlap with the sp hybrid orbital, sharing that electron, okay. And so what you see is that the way this is drawn out matches that observed geometry of beryllium compounds, which is linear, okay. This is linear as well. And so that kind of helps explain how that covalent bond really helps take it from the atomic orbital to that molecular geometry. All right. One side note is the sp orbitals are going to be higher in energy than the 1s orbital, but lower than the 2p. So if you were to write out this hybrid orbital diagram, you would draw in the sp box and fill that in as well. So an important note when we're talking about hybrid orbitals is that when we mix a number of atomic orbitals, we're always going to get the same number of hybrid orbitals. Okay, this is an extremely important concept to remember. So we can also look at other hybrid orbitals that we can form, like sp2, which means that we have one s orbital and two p orbitals that come together and form the sp2. And we can see that down here, where basically we form three sp2 orbitals. Okay, so we have three atomic orbitals that are coming together, and we have three sp2 hybrid orbitals. Okay, when those are put together, we get the trigonal planar structure. We can also have sp3, where we have one s, right, three p orbitals. That forms four sp3 orbitals, since we had four atomic orbitals initially. Those come together to form this tetrahedral structure. And so really we can look at a summary of this, where we have our atomic orbitals, the hybrid orbital set, what geometry that gives, and the degrees of separation between those compounds. So this is really just a model to describe the shape of a molecule with respect to it forming covalent bonds and the atomic orbitals. Okay. However, it does not work for elements that contain more than an octet of electrons. Okay. So here the model has really met its match at that point. Well, talking about covalent bonds, we always show the electron density existing between the two atoms. Okay, that means they're on that internuclear axis. Okay, which is shown here. Okay. These are what we call sigma bonds. Okay, these are going to have head-to-head overlap. They have cylindrical symmetry of the electron density about that internuclear axis. Right, so wherever they're kind of intersecting, it's right there on the axis. However, the electron density could be above and below the internuclear axis, and this is what we call a pi bond, okay, which is just formed between two perpendicular p orbitals. So if you kind of remove this middle area here in pink and remove this area, you'll see that you have two p orbitals shown here. Okay, one, and then the other is here. Okay, those overlap above and beyond, or above and below that internuclear axis to share electrons. Okay. And this is when you have a pi bond. So this is side-to-side overlap, and it's generally weaker than a sigma bond. So why are these important? Well, the reason why is because when we talk about single bonds like in H2 has just one sigma bond. In a double bond, basically you have one sigma bond plus you have one pi bond. All right. And then if you have a triple bond, you have one sigma bond plus two pi bonds. So single bonds are always sigma bonds because sigma bond overlap is greater. Okay, it results in a stronger bond and more energy lowering. So how do these bonds really exist is the next question. Well, we can take a look at how double and triple bonds are formed based on this theory. So based on the structure of ethylene, the 3 bond angles around the carbon are going to be 120 degrees. So 120 degrees here, 120 degrees to the other, and back. Okay. This suggests that we have sp2 hybridization. So if you just look here in this structure, it would be 120 degrees to here, 120 to here, and 120 there. Okay. So each carbon has a sigma bond with the other carbon, right? It forms a sigma bond here, and it has this carbon is going to form that sigma bond here. It also is going to form a sigma bond with each of the hydrogens. Okay. Carbon has 4 valence electrons, so each one has 1 electron left in the unhybridized p orbital, right? So it still has 1 electron here, which needs to be shared with the other carbon, and so you get this pi bond formation above and beyond, all right, above and below. And so it's important that you go back over this and really kind of understand how you get these double and triple bonds. Okay. For a triple bond with like acetylene, which is shown here, you have 2 sp orbitals, okay, which are going to form a sigma bond, and you have 2 pairs of p orbitals, which overlap in a pi fashion to form these 2 pi bonds. So you can see that you get the top and the bottom here, and then you get one up front, and there's actually one in the back there too as well. Okay. So real key there is that for every triple bond you have 1 sigma bond and 2 pi bonds. For a double bond you're going to have 1 sigma and 1 pi, and for a single bond you're going to have 1 sigma bond. So really the last thing we're going to talk about is resonance structures, delocalization, and pi bonding. Okay. So everything we've talked about so far has said the bonding electrons are going to be localized. All right. So sigma and pi electrons are associated totally with the 2 atoms that form that bond. So that brings us back to this whole resonance idea. Okay. Well, we can also look at another example, which is called benzene. Okay. And so we had been talking about ozone, which basically we said, okay, these electrons aren't necessarily localized, they're kind of delocalized. They're shared over this because it could exist as either state. So to describe the bonding in benzene, we use hybrid orbitals. Okay. So each carbon is surrounded by 3 atoms at 120 degrees, right? So if we pick this carbon, it's 120 degrees from here to here, from there to there, and from here to there, okay? It has 6 carbon-hydrogen bonds, right? 1, 2, 3, 4, 5, and 6. 6 carbon-carbon bonds, which are sigma bonds, and they're formed from the sp2 hybrid orbitals. So this leaves on each carbon a 2p orbital, and each contains 1 electron. All right, this is going to leave 6 electrons for carbon-carbon pi bonding. So what you would expect is that you would get 3 pi bonds like this, okay? But it could also be shown with those pi bonds rotating just one position. Right? So what really happens is we get delocalization of the electrons as they are spread out. And so in reality, the pi electrons in benzene are not localized. They're going to be delocalized and shared without. And so you get even distribution of the pi electrons in benzene, which makes it pretty stable. Okay? So you can see the sigma bonds with the carbon-carbon overlap and a carbon-hydrogen bond. The 2 p atomic orbitals then are still free. Okay? And so what happens is those are shared. And so you could either get this structure, which looks like this one, or you get the double bonds, pi bonds shown here. But what really happens is we have that resonance and they're delocalized. Okay, so that really sums up part 2. Part 3 will follow, which is molecular orbital theory. So make sure you go over this last bit. I know that the bonding orbitals can become very confusing. If you have questions, let me know.